Imagine standing near the rim of a crater at Mercury's North Pole. Above you, the sunlight strikes the high ground with a force that can heat exposed rock to about 430 degrees Celsius. A short distance below, however, the crater floor sits in permanent darkness, and some of that darkness is cold enough to freeze water. That image is difficult to comprehend when the first thing that comes to mind when thinking of Mercury is a ball in front of a huge fire. And it is. But Mercury isn't one enormous furnace. It's a stack of hostile environments pressed together. Blazing ground can overlook a shadow that hasn't seen sunlight for millions of years. A sealed habitat might hide beneath the surface, protected from the worst heat and radiation, and the ice could provide water, oxygen, and perhaps fuel. That sounds like an opportunity. It may also be a very expensive trap. A habitat there would need to keep its pressure, shed its waste heat, survive radiation, and protect every seal from abrasive dust. Its crew would have to dig, repair machinery, replace worn parts, and obtain whatever Mercury couldn't provide. And even the coldest crater doesn't make those challenges disappear. It merely changes which ones arrive first. So the real question isn't whether Mercury is hot. We know it is. It is whether a complete survival system could defeat all of Mercury's challenges at once, for long enough that rescue from Earth stopped being the backup plan. But before we decide whether that dark crater is shelter, we first need to ask what Mercury actually does to anything left outside. If you enjoy exploring questions like this with me, subscribing helps others find them too. Liking and sharing the video helps even more. Now, let's begin. You're not being unreasonable if you want to stop at the temperature. Mercury is the closest planet to the Sun, and its sunlit surface can reach about 800 degrees Fahrenheit, around 430 degrees Celsius. That's hot enough to make any talk of living there sound faintly ridiculous. Imagine the ground at local noon. White sunlight falls on bare rock beneath a black sky. There's no haze to soften the glare. No moving air carries heat away. The surface absorbs sunlight for a very long Mercury day, until the rock itself becomes a furnace. A person standing there in the open wouldn't have a difficult afternoon. They would have no survivable environment at all. The vacuum would already demand a pressure suit, and the exposed surface would add an extreme heat problem. Machinery, seals, electronics, cooling systems, everything would have to work while facing intense sunlight and radiating rock. At 800 degrees Fahrenheit, walking around unprotected is impossible, completely. And that obvious answer deserves to be granted before we make it more complicated. Mercury's sunlit ground is lethal. No clever wording turns 430 degrees Celsius into a pleasant day. But notice what the number actually describes. It belongs to exposed rock under direct sunlight. It doesn't mean every place on Mercury, at every latitude, in every shadow, reaches that same temperature. And it doesn't tell us what conditions might exist inside a sealed structure designed to keep the surface outside. This is a little like measuring the temperature of a stovetop and using it to judge the whole kitchen. The burner can injure you within seconds. That fact is real and useful. It still doesn't tell you the temperature beneath the counter, inside the refrigerator, or behind an insulated wall. One fierce measurement can settle the question of direct contact without settling every question about the room. Mercury gives us the same awkward distinction. Its hottest illuminated terrain proves that open survival fails. It does not prove that the entire planet is uniformly hot, because Mercury has almost no atmosphere to spread that heat around, nor does it decide, by itself, whether an engineered habitat could separate its interior from the surface conditions outside. So the easy rejection was reasonable. It was simply aimed at a person standing on bare rock in full sunlight. That person cannot survive, but a human habitat is built precisely because the place outside cannot support a human body. The hottest number on Mercury closes the door on the open surface. It doesn't yet close the case. Most people never imagine Mercury as a freezing place. The name brings up white sunlight, scorched rock, and heat fierce enough to destroy an unprotected body. Darkness seems like the obvious escape. Walk far enough from the glare, you might think, and the danger should ease. Instead, night brings a different way to die. NASA puts Mercury's nighttime surface temperature near minus 290 degrees Fahrenheit. That's about minus 180 Celsius. Cold enough that the dark side belongs beside some of the bitterest places in the solar system, even though the planet sits so close to the Sun. Imagine watching one patch of ground as daylight fades. The blinding surface dims, the rocks stop receiving sunlight, and the temperature keeps falling. There's no gentle evening and no comfortable middle waiting after sunset. The same world that can overwhelm you with heat in daylight becomes a black plain cold enough to break the easy idea that darkness means safety. Mercury gives you two lethal answers depending on where the Sun is. Stand in the light and your surroundings become brutally hot. Remain in darkness and the surface moves toward minus 290 degrees Fahrenheit or minus 180 Celsius. The correction to too hot is not safe. It's far too cold. That's the quiet absurdity of Mercury. If you tried to escape one extreme by moving away from it, you could end up heading toward the opposite extreme. A traveler chasing relief across the surface wouldn't find a broad, forgiving climate between them. Light and shadow divide the planet into conditions that defeat an exposed human body in different ways. The night side is not secretly comfortable. It isn't temperate, and darkness does not make it naturally protective. It only changes which problem reaches you first. On Earth, day and night usually feel like variations within one shared climate. Mercury does not offer that kind of moderation. With no substantial atmosphere to soften the change, sunlight and darkness press the surface toward opposite ends of the thermometer. So Mercury is not one giant furnace. It is a world split between two kinds of exposure, both fatal, with each half correcting the wrong assumption about the other. Something about this planet allows light and shadow to strike with almost nothing in between. You might still imagine Mercury as a desert with the weather turned up too high. A harsher Sahara, perhaps, where the days punish the ground and the nights lose all that heat again. But deserts have air. Mercury, for practical purposes, does not. NASA describes Mercury as having no substantial atmosphere. The European Space Agency says the same. A scattering of loose atoms surrounds the planet in what scientists call an exosphere. But that is nothing like the layer of gas wrapped around Earth. No useful blanket. No sky full of moving air to carry warmth from one place to another. On Earth, the ground warms the air above it. Winds move that air elsewhere. Clouds block some sunlight and slow some escaping heat. Oceans, soil, and moisture absorb energy, then release it over time. Even a dry desert belongs to this larger system. Its temperatures rise and fall inside an atmosphere that is always shifting heat around. Mercury's surface is far more exposed. Sunlight reaches bare rock without passing through a thick layer of air. When that light disappears, there is no atmosphere capable of bringing much warmth from somewhere else. Heat can move through the ground, but rock moves it slowly. Meanwhile, the surface loses energy by radiation, sending it away as invisible light. So location changes everything in a way that feels almost unfair. A ridge facing the sun receives direct energy. A nearby hollow may remain dark. Turn one slope away from the light, and you have changed the main source of heat without any cloud, wind, or passing weather system getting involved. The rock has no local forecast, it has geometry. Near Mercury's poles, some deep crater floors never see sunlight at all. Their rims can stand in the sun while darkness remains below. There are no storm fronts crossing between those places, no warm breeze wandering into the shadows. The shape of the ground and the angle of the sun do much of the work that weather does here. It is heat without weather. Once you see Mercury that way, the planet stops looking like an unusually violent desert. It becomes exposed rock responding directly to light and darkness, with almost no air between them to soften or redistribute the result. And that does not make shade safe. It does not make keeping people comfortable simple. It only removes one familiar part of the problem, the atmosphere itself. So if an airless world gives a human habitat anything for free, what does it actually give? You might hope Mercury gives us something to work with. A wisp of air, perhaps. Enough gas to provide a little pressure around a habitat. or take some of the burden off a spacesuit. It doesn't. Stand on Mercury and look through your helmet visor. Above the horizon, there is technically chemistry. Oxygen, sodium, hydrogen, helium, and potassium are all present. NASA and the European Space Agency describe this faint collection of particles as an exosphere. That word sounds reassuringly like atmosphere. On Mercury, it isn't. An atmosphere is a blanket of gas. Its countless molecules collide, build pressure, move heat, and produce weather. An exosphere is more like a few grains of flour floating through a large kitchen after someone has slammed a cupboard door. The grains exist. You could identify what they're made of, but you couldn't bake with the air. Mercury's particles are scattered so widely that they rarely meet. Some are knocked loose from the surface by sunlight, tiny impacts or charged particles streaming from the sun. Others arrive through interactions with that solar wind. They can linger for a while, fall back, or escape into space. The supply is continually disturbed and replenished, yet it never gathers into a useful layer of air. So there is no ambient pressure for a human body, no breathable mixture waiting to be filtered, no wind to carry warmth, and no weather to offer even an occasional change of conditions. If you opened a valve outside, Mercury's exosphere would not come rushing in. The gas inside would rush out. That distinction is important because thin atmosphere can suggest a difficult version of somewhere familiar. High mountains have thin air. Mars has an atmosphere so slight that a person still needs full protection, but it can push dust and produce weather. Mercury is farther along that scale, operationally close to open vacuum. Calling it an exosphere is scientifically accurate. Calling it air would be generous to the point of absurdity. Those oxygen atoms above the ground do not add up to a breath, any more than a few drops in a parking lot add up to a swimming pool. Mercury does have particles above its surface. It does have an exosphere. But for anyone standing behind that visor, the practical correction is simpler. Not an atmosphere at all. A habitat there cannot borrow Earth-like conditions from its surroundings. It has to bring them. And bring Earth turns out to be a surprisingly heavy phrase. It means bringing a pocket of air, keeping it at the right pressure, moving it around the cabin, and watching it for anything the crew should not be breathing. It means carrying water, cleaning that water, collecting waste, and recovering whatever can be used again. A bright little room on Mercury would look like shelter. In practice, it would be a machine making Earth conditions every second. NASA groups these jobs under a rather plain name: Environmental Control and Life Support Systems, or ECLSS. On the International Space Station, those systems control cabin pressure, supply oxygen, recover water, ventilate the living space, and handle waste. None of that happens because the walls are simply there. Pumps run, filters catch contaminants, fans keep air moving, sensors watch the mixture, valves open and close. The room stays habitable because machinery is continually doing the work that our planet usually does without asking for attention. You rarely notice that help here. Open a door, and the atmosphere does not drain into nothing. A small gap around a window may waste heat or make the room uncomfortable, but it does not turn the room into a medical emergency. Outside, there is more air, there is pressure, there is water somewhere nearby. Earth keeps meeting you halfway. Mercury would not. Every cabin, suit and rover would have to be an artificial Earth machine, not a shelter sitting inside natural air. A suit would carry its own pressure and oxygen. A rover could not merely transport you. It would have to preserve the small environment around your body while it moved. Even the connection between rover and habitat would matter, because opening one sealed space to another is an operation, not just walking through a door. That changes what ordinary hardware means. A seal is part of survival. So is a filter, a ventilation fan, an oxygen reserve, a pressure sensor, and every pipe carrying reclaimed water. A leak is not only damage to a building, it is the surrounding vacuum reaching into the one place where a human body can function. None of this makes a Mercury habitat impossible. Engineers already build systems that perform these jobs in space. The burden is that the jobs remain continuous. They need power, maintenance, spare parts and backups. because Mercury supplies no quiet background layer of support when something stops. So the small bright cabin on that black landscape would carry more than its crew. It would carry the pressure, air, water and sanitation of another world. Living there would mean keeping that borrowed piece of Earth alive every second. You might imagine the dangerous moments would be rare. A major rupture, a fire, some dramatic alarm that sends everyone running. Most days would be less cinematic than that. Someone would inspect a hatch, replace a worn valve, count oxygen reserves, and wonder whether a faint hiss was real or only the suit fan. Imagine a worker outside the habitat. The building is only a few steps away, but those steps cross open vacuum. The worker depends on a chain of ordinary-looking parts: gloves, joints, hoses, seals, batteries, radio, cooling loop. A damaged glove isn't inconvenient in the way a torn coat is inconvenient. It changes how long the person can safely remain outside. The hatch is just as important, so is the seal around it. Dust or wear in the wrong place could turn a routine return into careful, time-limited work. Inside, someone watches the pressure. Someone else prepares the second entrance or checks how much reserve air can be used. Nothing has to explode for the situation to become serious. That's the quiet claustrophobia of living there. The settlement can grow larger, and the machinery can become more reliable, but the machinery never becomes optional. Every room is part shelter and part spacecraft. Every trip outdoors begins with checking whether a small private atmosphere is still attached to your body. NASA's life support work treats leaks, consumables, and environmental control as continuing operations, because spaceflight never reaches a point where the crew can simply stop managing them. Mercury would make that temporary logic permanent. Spare parts wouldn't sit on a shelf as a comfort. They would be pieces of future breathing, cooling, pumping, and pressure control waiting for their turn. On Earth, a failed air conditioner can make a room miserable. A broken water pump can force people to leave. There is usually somewhere else to go, and the air keeps arriving without being ordered. On Mercury, leaving one machine means entering another. Habitat to suit, suit to rover, rover back to habitat. Safety is passed from one sealed system to the next, like a glass of water that can never be set down. So a settlement there wouldn't merely contain machines. It would behave like one enormous machine, with people living inside its moving parts. And once that machine has to stay awake without interruption, what happens when Mercury's own day lasts for months? A day still sounds manageable, even a terrible one. You expect morning, noon, evening, and then some relief when the sun finally slips below the horizon. Mercury doesn't offer that familiar rhythm. Its surface moves through time at a pace that makes an ordinary day feel almost brisk. NASA puts Mercury's rotation period at about 59 Earth days. One complete turn against the distant stars takes nearly 2 months here on Earth. Start the clock on a Monday, and Mercury is still working through that same rotation when 8 more Mondays have passed. It's mildly unnerving. The planet is turning. It just doesn't seem particularly committed to finishing. For a settlement, that isn't an interesting number to print on a wall. It's the pace at which the ground changes its orientation to space. The landscape turns so slowly that long exposure to light or darkness can outlast the schedules our bodies, buildings, and maintenance habits expect. Imagine watching the horizon through a protected window. On Earth, you can notice the sun move if you give it a little time. Shadows slide across a floor. A bright wall softens toward evening. On Mercury, the horizon seems reluctant to do anything at all. You could sleep, wake, work, repair equipment, eat several rather repetitive meals, sleep again, and still feel caught inside the same part of the cycle. That changes how people would plan. Equipment exposed to sunlight may need protection for long stretches. Equipment in darkness may stay cold long enough to make warming, lubrication, and battery care ongoing jobs. Repairs can't always wait for a convenient evening. Power systems can't treat daylight as a quick daily delivery. Crews would measure changing conditions in weeks. Their plans would have to survive shift handovers, tired people, delayed parts, and all the small mistakes that appear when a temporary condition refuses to be temporary. Rotation alone doesn't tell you exactly what every site experiences. Mercury's path around the Sun also changes the timing, and different landscapes would meet light in different ways. A crater wall, a ridge, and an open plain wouldn't share one neat schedule. 59 days describes the planet's turn against the stars, not every local hour of sunlight. But it gives us the scale. Mercury doesn't hurry from one condition into the next. It holds the surface there while machines keep working and people keep counting. Above them, the Sun seems almost fixed, and a sunrise begins by barely lifting itself from the stone. On Earth, sunrise feels dependable. Even after the longest night, the horizon eventually brightens. Sunset offers the same relief after a hot day. You may not enjoy waiting, but at least the wait is measured in hours. On Mercury, one sunrise follows the next about 176 Earth days later. That's nearly half an Earth year between sunrises at the same place. A crew watching the light crawl across the ground wouldn't be waiting for morning in any ordinary sense. They would be living through a season-sized stretch of one solar day. Imagine leaving a lamp over one side of a table for months. The lit side keeps receiving energy. The dark side keeps missing it. Mercury is far more complicated than a table, of course, but the planning problem begins there. Sunlight doesn't arrive for a shift, then politely leave when the equipment needs a break. It stays. Once it finally goes, the darkness stays too. That changes how a habitat experiences trouble. On Earth, an overheated building can often lean on the coming evening. Shade spreads, the air cools, and the heat source weakens. On Mercury, sunset can't be treated as tonight's rescue. Heat may keep falling on the same terrain for months, while radiators, insulation, and cooling systems carry the load without that familiar reset. A small loss of efficiency can't simply be endured until dusk. Dusk may still be months away. Then the long night reverses the burden. Solar heating fades, but it doesn't return the next morning. Equipment must remain warm and useful through darkness that outlasts any normal emergency plan. A temporary backup begins to look less like a backup and more like a campaign. Supplies aren't carrying you through the night. They're carrying you through a large piece of a year. That doesn't mean every location follows one simple clock. Near the poles, low sun angles, crater walls, and local terrain can produce very different patterns. A carefully chosen site might avoid some of the clean, punishing alternation found at more ordinary latitudes, but the 176-day solar cycle still tells us what kind of world this is. Light changes slowly enough that geography becomes part of the machinery. Where you place a habitat can affect survival almost as much as what you put inside it. And that may be the most tiring part. Sunrise and sunset stop feeling like rescue events. They become major operational transitions, rare enough to prepare for and slow enough to watch approaching, without receiving much immediate help. A crew could still speak of morning and evening. The words would survive. Their comforting meaning would not. On Mercury, the day-night cycle doesn't organize daily life. Daily life has to organize itself against a day that refuses to end. Once you accept that kind of day, batteries stop looking like an overnight solution. On Earth, backup power usually carries you through a short interruption, a few hours, perhaps a few days. Then the grid returns. The generator is refueled, or daylight reaches the solar panels again. Mercury offers no such comforting rhythm. Imagine stocking a remote cabin before a winter storm. You bring food, fuel, and enough firewood to last until the road opens. Now imagine that the storm lasts for months, and the road was never meant to open quickly. Every extra day changes the calculation. You need more supplies, more room to store them, and more equipment to protect the supplies you already have. A habitat on Mercury would face that same problem with energy and heat. During the long daylight, solar panels could produce power, but the habitat would also need to control the heat arriving from outside. It might store energy for later, move waste heat away, and keep delicate equipment within a narrow temperature range. None of those jobs is unusual by itself. The awkward part is how long the systems must keep doing them before conditions meaningfully change. Then darkness arrives just as slowly. Solar production falls away, but the habitat still needs electricity for air, water, communications, pumps, computers, and temperature control. Stored power is no longer a small bridge to morning. It becomes a campaign stockpile. The batteries, fuel cells, or other reserves must last through a long operating window with enough margin for faults and repairs. Insulation helps, of course, so does careful planning. But insulation doesn't make heat disappear, and planning doesn't create energy. Even a well-designed habitat would need somewhere for excess heat to go, and some dependable way to keep essential systems running when sunlight isn't available. The slower the outside world changes, the longer every reserve must carry the load. That doesn't make living on Mercury impossible. It makes the planet's clock a multiplier. A small inefficiency keeps costing energy for longer. A damaged component has more time to become serious. A conservative safety margin becomes heavier, larger, and more expensive. Ordinary backup systems start looking like expedition hardware. And all of this appears on the budget sheet before anyone adds radiation exposure, mining equipment, or the trouble of moving supplies between worlds. So if batteries and insulation can only carry the burden, does Mercury offer any natural protection that might ease it? The word magnetosphere sounds like good news. You hear it and imagine a clear dome around Mercury, turning aside whatever the sun throws at the planet. After all the machinery we've already had to bring with us, a little natural protection would be welcome. And the field is real. Mercury has a global magnetic field, which makes it unusual among the small, rocky worlds. NASA puts its strength at the surface at roughly 1% of Earth's. That comparison is easy to hear and then quietly ignore, because magnetosphere still sounds like magnetosphere. But 1% is doing a lot of work here. Think of two roofs in heavy rain. One is the roof over your house. The other is a thin sheet held above part of a campsite. Both change where the water goes. Both provide some cover. Only one lets you forget about the storm while you make coffee. Mercury's magnetic field can redirect charged particles and shape the space around the planet. Spacecraft can detect that structure. Scientists can watch it respond to conditions coming from the sun. It gives Mercury a magnetic tail and a complicated local particle environment. None of that is imaginary, and none of it is trivial if you're trying to understand how a small planet kept a magnetic field at all. It just doesn't follow that people on the surface inherit Earth-like shelter. Earth's field is much stronger, and it works alongside a thick atmosphere. Mercury offers neither that combination nor anything close to it. Its weak field changes the paths of some particles, but the word magnetosphere shouldn't be stretched into a roof over a settlement. We also shouldn't pretend one neat radiation number applies everywhere. Exposure would depend on location, shielding, solar conditions, and how long people stayed there. So the fair version is slightly awkward. Mercury really is magnetized. Its field is scientifically valuable, surprisingly persistent and strong enough to shape its surroundings. But a field can be fascinating without being generous. For anyone trying to live there, the practical protection would still have to come from mass, design, monitoring, and careful limits on exposure. The natural field may alter the risk around the edges. It doesn't remove the risk stack waiting behind it. Mercury has a magnetosphere. It just isn't the kind you can live under. That verdict doesn't make Mercury's magnetic field unimportant. It only means we have to ask the field the right question. A map can tell you something remarkable about a planet without doubling as a roof for the people standing on it. NASA's Messenger spacecraft gave scientists that kind of map. Its instruments followed the magnetic field around Mercury and found that the field isn't centered neatly inside the planet. It is shifted northward, so the magnetic surroundings are uneven, with a different shape in the north than in the south. That offset is a useful clue. A planet's magnetic field comes from motion deep inside it, where electrically conducting material moves through the core. We can't lower a camera into Mercury and watch that happen. The field above the surface is one of the few traces the hidden interior leaves where instruments can reach it. By measuring the field carefully, scientists can test ideas about the size, structure, and behavior of Mercury's core. And Mercury is an especially interesting case because it is small and close to the Sun. You might expect such a world to have cooled into magnetic silence long ago. Yet something inside it is still producing a global field. The Messenger didn't produce a complete map of the interior, but it gave planetary scientists a much better constraint. The northward offset is real evidence about how this little planet works. That deserves more than a shrug. Instrument traces and field lines may look like thin curves on a screen, but they record an active planetary system. They show Mercury meeting the solar wind, redirecting charged particles, and responding to the space around it. Scientifically, that is rich material. But none of those curves becomes a ceiling. Knowing that the field is offset doesn't identify a hemisphere where an exposed crew could simply relax. A region can be magnetically different without being safe. Messenger measured the planet's environment. It did not certify a natural shelter for human bodies. It helps to keep those two claims separate. Mercury's field is valuable because it reveals the planet. It is inadequate because human survival asks for something else: dependable reduction of radiation and particle exposure across changing solar conditions, locations, and lengths of stay. So the field belongs in any complete account of Mercury, just not in the role of rescuer. It sharpens the science while leaving the engineering problem exactly where it was. Once people enter the plan, the hazard map grows beyond magnetism to radiation, heat, dust, vacuum, and the long task of building protection that the planet does not provide. It's tempting to turn Mercury into a checklist with one enormous box at the top. Solve radiation, tick the box, and perhaps everything below it becomes manageable. But Mercury doesn't behave like that. Radiation is real, and protection has to work through changing solar conditions. Yet the shield cannot exist by itself. It needs mass. Mass needs transport. Transport needs fuel and power. The equipment carrying all of that must also survive sharp temperature changes, hold pressure in a vacuum, and remain repairable when the nearest spare part is back on Earth. You can imagine the checklist on the wall. Pressure, temperature, radiation, power, dust, food, water, repairs. Fix one box, and none of the others politely disappear. The fix may even make another box harder. More shielding adds weight. Burying equipment can reduce exposure, but excavation demands machinery, energy, and maintenance. Cooling protects electronics and people, but the cooling system becomes another thing that cannot be allowed to fail. This is the move from thinking about one variable to thinking about a stack. NASA's Human Research Program treats spaceflight hazards in much the same way. Radiation sits beside hostile environments, isolation and operational strain because crews experience them together. A tired person in a damaged habitat doesn't get to solve the radiation problem first, then move calmly to the pressure leak. The hazards share the same room, draw on the same limited supplies, and compete for the same pair of hands. That human part changes the risk. On Mercury, survival would depend on systems almost every second. Air, temperature control, power, communication, shielding, and medical support would all be manufactured conditions. Isolation then changes what a small failure means. A broken pump is also a repair job, a demand on spare parts, a drain on power, and a decision made far from immediate help. Even a successful repair may consume the reserve meant for the next failure. There is no single number that captures Mercury's radiation risk for every crew, shelter, route, solar event, and length of stay. And even a good radiation estimate would describe only one layer of the mission. Mercury keeps making each partial solution inherit several other costs. So the serious difficulty is accumulation. Nothing has to become theatrical. Ordinary engineering problems are quite enough when they arrive together, depend on one another, and leave very little room for a bad afternoon. If Mercury offers any genuine loophole in this stack, where does it first appear? You might expect Mercury's answer to be nowhere. It is the closest planet to the Sun, so every patch of ground should eventually be exposed. Morning arrives, shadows move, and any hiding place loses the argument. But Mercury barely leans. NASA puts its axial tilt at about 2 degrees. Imagine a globe held almost perfectly upright as it travels around the Sun. Earth leans by more than 23 degrees, which carries sunlight farther north and south as the seasons change. Mercury's much smaller lean keeps the Sun low on the horizon near its poles, year after year. That small tilt is enough to create a very unusual kind of darkness. Imagine yourself standing near Mercury's North Pole beside a deep crater. The surrounding ground may be brightly lit. The crater rim may catch the Sun as a sharp white line, but the Sun never climbs far above your horizon. If the crater is deep enough and its rim has the right shape, that low light cannot reach the floor. It is a little like sunlight passing over a high garden wall in winter. The upper bricks glow while the ground tucked close behind them stays dark. Now make the wall circular, lower the Sun until it barely clears the horizon, and keep its path confined to almost the same shallow angle. The shadow stops being a passing part of the day. It becomes part of the terrain. Mercury's thin atmosphere cannot spread much warmth into that darkness. There is no weather system pushing clouds around, and no thick blanket of air carrying heat from a sunlit slope into the crater below. Near the poles, the contest is mostly geometric. The Sun's angle, the height of the rim, the depth of the crater, and the direction each surface faces. A few meters of rock in the right place can decide whether sunlight arrives at all. That does not make every polar crater safe. Many slopes still receive sunlight. A shadowed floor can present other problems, and darkness by itself is not comfort. It does not supply power, shielding, level ground, or an easy route in and out. Still, this is Mercury's first precise exception. The planet does not offer shelter by becoming gentler. It offers a few places where its almost upright spin lets solid rock interrupt the Sun. Nearby ridges can stand in full daylight, while, just below them, the same crater floor is missed again and again. The planet turns. Mercury circles the Sun, the rim glows, and the ground beneath it remains under its dark stone lid. It's easy to hear shadow and imagine something temporary. A cool patch that slides across the ground, then disappears when the light changes. But on Mercury, some polar shadows are closer to landscapes. They have boundaries, depth, and a kind of permanence that can last through every turn of the planet. Now look across the lip of a deep crater. The rim in front of you is blazing white under the nearby Sun. The rock is taking the full force of sunlight at Mercury's distance, yet a short way below, the crater bowl is black. Not dim, not waiting for evening. The Sun never truly reaches parts of that floor. The crater's own shape does the work. Sunlight approaches the pole at such a low angle that the high rim blocks it. It's like standing behind a wall when the Sun is barely above the horizon, except this wall is made of ancient impact rock, and the protected ground lies deep beneath it. As Mercury moves through its days and years, the exact lighting around the crater changes. The deepest shadow remains. NASA's maps of Mercury's poles show these permanently shadowed craters gathered around both ends of the planet. They aren't passing dark marks in a photograph. They're stable topographic environments, created by the lasting relationship between the low Sun and the crater walls. A floor can remain hidden while exposed ground nearby continues to bake. That closeness is the unsettling part. You don't travel from a furnace to a freezer by crossing half a planet. In some places, the change may lie between the brilliant upper rim and the darkness directly beneath it. Near Sun heat above, a durable cold trap below. The boundary is carved into the ground. That doesn't make the crater comfortable. The floor may be rough, steep, difficult to reach, and completely cut off from direct sunlight. Calling it habitable would race far beyond the evidence. Even calling it easy terrain would be generous. Cold is only one condition, and surviving somewhere requires many conditions to cooperate. Still, the shadow turns a geometric loophole into a real place. There are actual patches of Mercury where the usual idea of the planet fails. The Sun can dominate almost everything around them and still be stopped by a ridge of rock. So Mercury can keep a furnace and a freezer almost side by side. One glows in fierce daylight, the other sits beneath it, calm, black, and old. The heat is obvious, the darkness is stable. What remains uncertain is what that darkness has managed to preserve. That uncertainty changes the answer, though only a little. Until now, Mercury has made refusal easy. Too much heat, too much radiation, almost no atmosphere, a day that lasts for months. You could stop there and feel reasonably certain that nobody should build a home on this planet. The poles make that certainty harder to defend. They don't give Mercury a friendly climate. They give it a narrow arrangement of rock and sunlight that may be worth examining. A whole planet can remain brutally hostile, while one small patch offers a combination found nowhere else. Imagine an outpost tucked low inside a polar crater. Its location isn't defined by pleasant weather. It's defined by angles. The floor stays out of direct sunlight. A nearby ridge may rise into long periods of light. Move the site too far in either direction, and the arrangement falls apart. Down below, darkness. Higher up, access to solar energy. Between them, a distance that might be useful, or might prove deeply inconvenient. This is a rather grudging maybe. Mercury hasn't become welcoming. It has simply produced one place where absolutely not is no longer the only defensible answer. And that may be the first serious concession the evidence has forced from us. Average conditions can tell you what most of a world is like. They can't always tell you whether every local configuration fails. On Mercury, topography creates the opening. A crater rim blocks the sun in one place while catching it nearby. Geometry tells us more than the planet's reputation. But a loophole isn't a solution. Permanent darkness brings its own extremes. Nearby light is only useful if people can reach it, capture it, and move that energy where it's needed. A promising map location can become a terrible engineering site once slopes, distances, ground conditions, and equipment enter the plan. So we shouldn't call these polar niches safe. We shouldn't call them easy, and we certainly shouldn't call them ready for settlement. What we can say is narrower and more interesting. Mercury contains at least one kind of place where survival deserves a proper audit. The question survives. Barely, perhaps, but for a defensible reason. And now the burden shifts from planetary averages to the dark ground itself. What has that shadow preserved, and what would it cost to use it? Ice on Mercury sounds like a mistake. This is the planet closest to the Sun, where sunlit ground can become hot enough to melt lead. Yet inside some polar craters, the evidence points to something wonderfully ordinary: frozen water. This didn't begin as a hopeful guess from people imagining future bases. Radar observations had already revealed unusually bright patches near Mercury's poles. Those patches lined up with places sunlight could not reach. Interesting, certainly, but radar alone couldn't settle exactly what was hiding there. Bright radar echoes can tell you that something unusual is present. They don't give you a neat label. Then NASA's Messenger spacecraft entered orbit around Mercury in 2011. It spent years examining the planet from above. Its instruments mapped the crater floors, measured their temperatures, studied how the deposits reflected light, and counted neutrons escaping from the surface. That last measurement sounds rather far removed from a glass of water, but hydrogen changes the neutron signal coming from the ground, and water contains hydrogen. When Messenger examined the bright polar deposits, the neutron measurements matched the pattern scientists expected from large amounts of water ice. The temperature maps supported the same explanation. So did the measurements of reflected light. You weren't looking at one suggestive clue being stretched into a convenient story. Different instruments, measuring different properties, kept pointing toward the same material. Each clue covered a weakness in the others. NASA's mission summary puts the conclusion plainly. Mercury's polar deposits are dominantly water ice. That is mission-grade evidence. The idea had moved beyond an intriguing radar pattern. A spacecraft had gone there, measured the deposits several ways, and found a consistent answer. Dominantly still leaves room for mess. Some ice may sit beneath a dark insulating layer. Some deposits may contain other frozen compounds or rocky material. The ice isn't necessarily clean, exposed, or spread evenly across every shadowed floor. Messenger showed that water ice is there. It didn't hand us a mining plan. Even so, water changes the human argument immediately. A cold place with no useful material is an unusual shelter. A cold place holding water is something else. Crews need water for drinking and sanitation. It can support plant growth. Split apart, it can provide oxygen and ingredients used in rocket propellant. Suddenly, the crater contains material a crew would otherwise have to bring from somewhere else. None of that makes the deposits easy to reach or use. It does make them worth treating as a possible resource rather than a curiosity. In Messenger's orbital data, a black crater floor became more than an absence of sunlight. It became a natural freezer inside the inner solar system, quietly holding one of the most useful substances a crew could find. That sounds like an astonishing bargain. Mercury has already done the cold storage. The water is sitting there, close to the surface, on a planet where every kilogram brought from elsewhere would be expensive. Then you look at the crater itself. Permanent darkness preserves the ice by denying it sunlight. No direct sunlight reaches the floor, so the deposit can remain cold for immense stretches of time. But that same darkness also removes the easiest source of local solar power. The place holding the resource is the place where solar panels can't simply unfold beside the equipment and get to work. Mercury has tucked its help inside its harshest local environment. Think of a freezer locked inside a furnace. Outside the crater, sunlight is fierce enough to heat Mercury's surface far beyond the boiling point of water. Down inside, the ground can stay cold enough for ice to survive. The boundary between them may cover a modest distance, but the working conditions change sharply. Sunlight and ice no longer occupy the same easy place. That separation creates a systems problem. Machines on the crater floor need energy to dig, warm, process, and move material. They also have to function across cryogenic terrain, where the ground and equipment can sit at temperatures that make ordinary lubricants, batteries, seals, and cables troublesome. The ice survives because the floor is so cold. Any extraction system inherits that cold the moment it reaches the resource. Power could still come from somewhere else. Solar arrays might stand on illuminated ground, with electricity carried into the shadow. Light could be redirected. Other power sources could be used. None of this makes extraction impossible. It simply means the first appealing idea, ice beside a convenient solar-powered base, falls apart when you place it on the actual landscape. Even moving the material changes the problem rather than ending it. Ice brought toward warmer, brighter ground must be kept from escaping as vapor. Equipment may need to cross steep crater walls or work through long stretches without direct contact with the sun. Every solution adds mass, machinery, and another thing that has to keep working far from home. So Mercury's polar ice really could reduce one enormous burden. A crew might not need to import every drop of water it uses, but the planet charges for that advantage in another currency: power delivery, cold-resistant machinery, and access across difficult ground. The dark crater floor holds what you need most while refusing to power the tools that would reach it. The same shadow that saves the ice also sets the price of touching it. Seeing ice on a map is one thing. Putting it into a tank is another. Between those two moments sits an entire industrial system, and every part of it has to arrive from somewhere else. A machine would first need to reach the deposit without sliding, tipping, or burying itself. Then it would have to dig into material that has been frozen for ages. The ice may be mixed through soil rather than waiting in clean, convenient blocks. So the machine could end up collecting far more dirt than water, then carrying that material to equipment that can separate the two. That separation takes heat. You warm the soil, release the frozen water, capture the vapor, and cool it into a form you can store. None of that happens for free. Pumps need power. Seals need to hold. Dust has to stay out of moving parts. Pipes must survive repeated heating and cooling without cracking. And if one small component fails, the repair machine needs a repair machine. Even then, you don't yet have shelter or fuel. You have water in a container. Turning some of it into oxygen for breathing, or hydrogen and oxygen for propellant, requires more equipment and more energy. Using it as radiation shielding means moving large amounts of it to wherever people live. Water is wonderfully useful partly because it is heavy. Unfortunately, heavy things are awkward to haul across a crater. This doesn't make Mercury's ice worthless, far from it. A local supply could still be cheaper than launching the same mass from Earth, especially once a base was established. The awkward part is that the first useful kilogram may demand many kilograms of machinery beforehand. Rovers, cables, processing units, storage tanks, spare parts, perhaps relay stations or powered routes across the surface. So the deposit isn't a ready-made oasis. It is more like a locked warehouse whose contents are valuable enough to justify building the road, the quay, the lights, and the loading dock. The ice can support survival only after a chain of hardware turns frozen ground into something a crew can drink, breathe, burn, or stack around a habitat. And Mercury is not gentle with long chains of equipment. Before imagining people depending on this machinery, what did our robotic missions reveal about the difficulty of reaching and working around the planet at all? For a long time, Mercury was the sort of place we discussed with more confidence than evidence. The Moon had been walked on. Mars had landers sitting in its dust. Mercury had given us a few brief encounters, then gone back to being a bright, difficult dot near the Sun. That changes what we can say about survival there. A quick visit can reveal a coastline. It cannot tell you how the weather changes, where the ground differs, or whether one surprising reading is common or merely local. You need to return to the same places. You need different instruments looking at the same world. Most of all, you need time. NASA's Messenger spacecraft supplied that time. It became the first spacecraft to orbit Mercury, then remained there for more than 4 years. 4 years of circling, measuring, comparing, and coming around again. That wasn't a glimpse through an open door. It was patient observation of an entire planet. Messenger measured Mercury's surface composition and mapped its geology. It followed the planet's magnetic field. It examined the bright radar deposits hidden near the poles and helped establish what those deposits contained. Each kind of measurement checked the others. A feature seen in an image could be compared with its chemistry, its location, its temperature conditions, and the shape of the surrounding ground. This is how a planet stops being mostly guesswork. Not because one institution declares it understood, and not because one dramatic measurement settles everything. The evidence becomes stronger because the spacecraft keeps passing overhead, gathering another view under different conditions. Odd results can be checked. Broad patterns can separate themselves from noise. More than 4 years is long enough for that evidence base to grow up. Mercury became a world with global maps, repeated measurements, and several connected lines of evidence. It could finally answer detailed questions about what it is, rather than merely inviting clever guesses about what it might be. None of this gives us a finished habitat design. An orbiter cannot prove that a drill will survive, that a power system will stay reliable, or that people can live beside those polar deposits. Those remain engineering questions, and some may only yield to machines working on the ground. But the argument now begins from a measured planet. Before anyone could sensibly imagine a base, Messenger made the map trustworthy enough to show where that imagination had earned the right to begin. That trustworthy map changed more than our confidence. It changed what kinds of claims we're allowed to make. Before Messenger, Mercury could serve as a blank screen. Almost any survival idea might sound possible if the planet stayed blurry enough. Messenger took away that comfort. NASA's summary of the mission points to 4 broad results: surface composition, geological history, magnetic structure, and confirmation of water ice near the poles. Those aren't decorative details. Together, they tell us what sort of world a machine, a shelter, or a person would actually have to deal with. Think of choosing a place to camp from an old photograph. You might see a flat patch and decide it looks suitable. Then someone hands you a proper map. Now you can see the slope, the exposed rock, the flood channel, and the distance to water. The map hasn't built your tent. It has simply removed several pleasant ways to be wrong. Mercury's surface composition affects any survival plan because that plan depends on the material beneath it. Rock isn't just scenery. It may become shielding, construction feedstock, or a source of useful elements, but each proposal has to begin with measured chemistry. not a convenient guess about what the ground ought to contain. Its geological history helps for a different reason. Craters, volcanic plains, and old faults reveal how the surface formed and where different materials ended up. They help us distinguish a location that merely looks quiet from one whose structure and past are actually understood. Then there's the magnetic field. Mercury has one, weak but global, and Messenger mapped its shape and its interaction with the solar wind. That doesn't hand future settlers a ready-made shield. It does tell engineers that the radiation environment isn't a simple copy of empty space or of the moon. The planet changes the charged particles around it, unevenly and sometimes violently. And at the poles, radar hints became something firmer. Messenger found evidence consistent with water ice inside permanently shadowed craters, along with dark material covering some deposits. That gives the loophole a physical address. Water, shade, and comparatively stable cold occupy real places on Mercury. They're not ingredients added because the story needs them. Still, a map of ice isn't a glass of water. We don't yet know how easily those deposits could be reached, excavated, cleaned, or used for years without ruining the very conditions that preserve them. Orbital evidence can narrow the problem. It cannot quietly solve the machinery. So Messenger did something less glamorous and more useful than making Mercury look impressive. It made the planet specific. The loophole is real enough to survive contact with the evidence, and the same evidence makes its costs impossible to hide. It's tempting to put robotic trouble in a separate category. An orbiter is a delicate science machine after all. A future settlement would be larger, sturdier, and built for the place. So perhaps the difficulties faced by spacecraft tell us very little about what people would face. But look at Bepi Colombo before anyone even enters the conversation. The spacecraft had to leave Earth wrapped in reflective protection, with careful control over which surfaces could face Mercury and for how long. According to the European Space Agency's engineering notes, some outside surfaces may encounter temperatures around 842 degrees Fahrenheit, about 450 degrees Celsius. That doesn't mean an orbiter and a habitat are the same engineering problem. They aren't. An orbiter moves through changing sunlight and carries sensitive instruments. A settlement could hide equipment, bury rooms, and use far more mass. It could choose a better location and stay there. Still, the machine gives us a useful warning. Before it carries air, water, food, people, or even a comfortable chair, hardware near Mercury already has to devote a large part of its design to surviving heat. Reflective coverings must reject sunlight. Radiators must release waste heat without staring at the hot planet. Instruments need shelter. Orientation becomes part of survival, because pointing the wrong surface the wrong way can turn ordinary operation into overheating. A human system inherits those jobs and then adds more. People make heat simply by being alive. So do pumps, lights, computers, kitchens, air scrubbers, water processors, and every motor that keeps the habitat running. All of that heat has to go somewhere. On Earth, the air and ground quietly help. Near Mercury, the architecture has to manage the whole transaction with much less forgiveness. Bepi Colombo doesn't prove that people cannot live there. It shows something more modest and more useful. Mercury starts charging an engineering price before the passenger list contains a single name. A settlement may pay that price with shade, insulation, radiators, buried rooms, and careful timing. But it still pays. The obvious hope is to stop carrying every protective layer from Earth and use Mercury itself. There is plenty of rock and dust nearby, yet local material only helps if machines can dig it, move it, shape it, and maintain the equipment doing the work. So does Mercury's own ground truly reduce the burden, or does it merely move that burden into another set of machines? Use local materials sounds almost too sensible to argue with. If you're standing on a world covered in rock and dust, why carry every kilogram of protection across millions of miles? The ground is already there. Let Mercury pay part of its own construction bill. That hope isn't foolish. NASA's Messenger spacecraft gave us our first detailed view of Mercury's chemistry and volcanic past. Its measurements showed that the surface isn't some unknown grey powder we can only guess about. Mercury has a varied crust shaped by ancient lava and billions of years of impacts. We now know enough about that material to discuss possible uses without simply inventing them. The easiest use may also be the least glamorous: pile dirt over a habitat. A thick layer of regolith could place ordinary mass between the crew and the radiation above them. It might also help soften the wild temperature changes near the surface. The material wouldn't need to become a polished beam, a perfect tile, or a clever new alloy. It would mostly need to be moved into the right place and kept there. A sandbag can be valuable without pretending to be a factory. Some of Mercury's surface material might also become feedstock for rough construction processes. It could perhaps be crushed, sorted, heated, or bound into useful shapes. But each of those words hides a machine. Crushing needs tools that survive abrasive dust. Sorting needs energy and equipment. Heating needs a controlled process. Even making a crude block means choosing the right material, moving it, and checking that it behaves as expected. None of this proves the work is impossible. It only keeps a plausible source of help from quietly turning into a promise of finished products. And this is where the phrase local resources becomes a little slippery. The material may be local, the useful object is not. A plain of regolith can look like a warehouse with no walls. In practice, it's closer to a delivery of unsorted ingredients with no labels, no kitchen, and no guarantee that the recipe works. That doesn't make the ingredients worthless. It means the settlement still has to supply the knowledge, power, machinery, spare parts and labor that turn them into protection. So Mercury's ground could reduce what must arrive from Earth, especially when the job only calls for bulk shielding or rough process material. That is real help. It's simply not self-sufficiency hiding under a layer of dust. The dirt is free only until you try to make it useful. It's tempting to imagine a very simple job. Park the habitat, push some nearby soil over it, and call the radiation problem handled. On Earth, that might mean a loader, a few workers, and an afternoon of unpleasant dust. The pile is already there. How expensive could moving it be? Then Mercury quietly slides the construction invoice across the table. Before one layer of shielding reaches the habitat, something has to excavate it. That machine needs traction in loose ground, even though Mercury's gravity is only about 38% of Earth's. Its joints, bearings, cables, and electronics have to keep working in a vacuum. Lubricants behave differently there. Fine grains can creep into seals and moving parts. Sunlit equipment can become extremely hot, while shaded parts nearby remain bitterly cold. There's no mild morning when the crew can catch up under easier conditions. Once the soil is dug up, it still has to move. A loader, conveyor, hopper, or hauling vehicle must carry it without throwing abrasive dust across every surface that needs to stay clean. The machinery needs power. It needs cooling. It needs somewhere protected for repairs. And if a belt tears or a wheel motor fails, a person or another machine has to reach it, diagnose it, and replace the damaged part. Then comes placement. Loose material can't simply be wished into a stable roof. It may need bags, bins, retaining walls, compacted layers, or another structure to keep it where it belongs. Those containers and supports add more equipment, more seals, more connections, and more things that can shift as temperatures change. Even after the shielding is in place, someone has to inspect and maintain it. You don't want to discover that vibration, settling, or a failed wall has quietly thinned the cover over an occupied room. Every ordinary construction verb becomes a Mercury verb. Digging on Mercury, hauling on Mercury, loading, sealing, repairing, and checking on Mercury. The raw mass may travel only a few hundred yards, but the machines doing the work have crossed an entirely different distance, from a friendly work site to an airless world where heat, cold, dust, and radiation all reach the equipment at once. Local shielding could still become a major advantage. Over years of operation, moving nearby soil may be far cheaper than launching the same mass from Earth. The larger the settlement grows, the more valuable that difference becomes. But those savings arrive after a working industrial system exists, not before it. A bunker built from Mercury's own ground is possible in principle. It just isn't a free bunker. Before the dirt can protect anyone, the settlement has to earn every layer of it. Imagine that shelter a few years later. The walls are thick. The living space sits behind enough local material to cut down the radiation reaching the people inside. From the doorway, it may finally look as though the hard part has been turned into architecture. The danger is outside. The bunker is here. Job done. Except the bunker has inherited an entire machine world. Excavators still need to dig. Haulers still need to move material. Motors drive their wheels, joints, pumps and tools. Dust gets into seals, bearings wear down, filters clog. Electronics need cooling. Broken parts have to be found, removed and replaced by someone or something able to work outside. Even a finished wall may need inspection after the ground shifts or repeated temperature changes strain the structure. The wall can sit quietly. The equipment behind it rarely gets that luxury. None of that makes local shielding a bad idea. It means the protection comes from an active system, not from a convenient pile that happened to be sitting in the right shape. A natural cave gives you a boundary before you switch on a machine. A manufactured shield gives you a boundary because machines have already done the work, and because enough of that industrial chain remains healthy to repair or extend it later. That difference changes the workload. The shelter may look still, but the safety around it has a pulse. Power runs the digging equipment. Power moves the loads. Power supports workshops, tools, sensors, spare part production, and the machines that service other machines. Every repair also needs trained attention, whether that comes from a person nearby or a robot guided from somewhere safer. If the settlement grows, so does that hidden network. More protected space means more material handled, more equipment hours, more worn components, and more maintenance. And radiation shielding is only one bill. A thick wall doesn't provide breathable air. It doesn't move heat away from living quarters. It doesn't bring food, water, or replacement hardware across space. Those problems remain, each with its own equipment and its own appetite for dependable energy. The bunker may reduce one danger without making the settlement independent of the machines around it. So the sturdy shelter is real enough. It just rests on something less visible, a working industrial system that cannot casually stop. Mercury may supply the mass, but the settlement must continually supply the work. Fortunately, Mercury sits painfully close to the Sun, under light far stronger than anything reaching Earth. Does that at least make reliable power easy? For once, Mercury gives us an answer that sounds genuinely helpful. Yes, all that sunlight is a remarkable source of energy. ESA's engineers had to account for it while designing Bepi Colombo, the spacecraft now traveling through Mercury's neighborhood. Around the planet, sunlight is about 11 times more intense than it is near Earth. 11 times. A solar panel there can receive in 1 square meter what would take roughly 11 square meters to catch at Earth's distance, assuming the same angle and no other losses. That doesn't mean every panel automatically produces 11 times the electricity. Panels have efficiency limits, and the angle of the sun still changes the output. Dust, shadows, and location affect it too, but the incoming energy is real. On illuminated ground, there is an enormous amount of it waiting to be collected. Imagine a solar farm stretched across a bright ridge. No clouds pass overhead. There's no weather in the usual sense. The sun hangs against a black sky, so bright that ordinary daylight suddenly seems rather modest. For equipment that needs power for digging, processing rock, pumping fluids, or keeping a buried settlement alive, this is not a minor consolation. It is one of Mercury's strongest practical advantages. And it arrives exactly where the demand would be high. Excavators need motors. Refining rock takes energy. Life support systems cannot simply take the afternoon off. A settlement that depends on machines would want a large, steady supply. And Mercury appears to place an extraordinary source directly above the worksite. We should be fair to the planet here. Its closeness to the Sun is usually presented as a problem, and often it is. But closeness also means that a relatively small collecting area could intercept a great deal of solar energy. That could reduce how much panel surface must be manufactured, carried, unfolded, cleaned, or repaired for a given amount of incoming light. When nearly every kilogram and every moving part has a cost, that is a useful gift. Still, sunlight is available only where it actually falls. Mercury has night, shadows, steep crater walls, and terrain facing the wrong way. Strong sunlight is not the same thing as uninterrupted power everywhere. Storage, transmission, and careful placement would remain part of the design. But on a ridge in full daylight, those qualifications can wait briefly. The ground is flooded with nearly 11 Earths worth of sunlight, and a field of dark panels turns toward it. Mercury finally looks generous, rich in power, silent beneath a sun that seems almost close enough to touch. And for one quiet moment, the engineering seems almost kind. Put the panels in sunlight, turn them toward the sun, and let Mercury do the rest. After all the trouble of carrying fuel and building storage, power appears to be the easy part. You can almost hear the planners relaxing. Then look at the panel itself, sitting there beneath that enormous light. On Earth, a solar panel can spend decades on a roof. It gets hot in summer, certainly, but the air around it helps carry heat away. A breeze crosses the glass. Cooler air moves behind the frame. The roof and its supports can take away some heat as well. On Mercury, there's no breeze. No cool air slips behind the panel. An exposed machine has to lose its heat mainly by sending it away as radiation. That's an awkward job when the sun keeps pouring energy into every surface facing it. The solar cells absorb some of that energy and turn it into electricity. They can't turn all of it into electricity. The remainder becomes heat, warming the cells, the wiring, the supports, and the machinery connected to them. Even equipment beside the panel has to cope with that hot, bright neighborhood. Bepi Colombo had to live with this problem before it ever reached Mercury. The European Space Agency reports that some surfaces on the spacecraft must endure temperatures around 842 degrees Fahrenheit, about 450 degrees Celsius. That is hot enough to make familiar ideas about outdoor equipment feel slightly ridiculous. Its protective layers, coatings, radiators, and carefully angled solar arrays exist because ordinary spacecraft hardware couldn't simply sit there and carry on. Parts could warp or weaken. Solar cells could lose efficiency. Electronics could fail. A settlement's power system would meet the same bargain on a much larger scale. Panels could be tilted away from the harshest angle. Engineers could choose reflective coatings and heat-resistant materials. They could add cooling systems or place radiators where those radiators have a clear view of colder sky. They might separate sensitive equipment from the hottest collectors instead of packing everything neatly together. All of that is possible. None of it makes solar power useless on Mercury. The sunlight remains an extraordinary energy source, and careful hardware could harvest it. But more sunlight isn't free when the collector has to survive inside it. Each panel becomes part generator and part oven tray. More incoming energy can mean more electrical power, while also demanding more heat rejection, more protective material, and more care over where every cable, joint, and control box goes. So Mercury's generous sunlight comes with a wonderfully unhelpful condition. The bright ground is rich in power. The deep shadows may hold the materials you need, and those two useful places may not be the same place. Imagine a ridge near Mercury's north pole blazing in sunlight. Solar panels line the high ground, where they can see the sun and make power. Just below them, the crater floor sits in permanent darkness. That is where the ice may be, one ridge glowing above, one dark bowl below. The whole base begins with that split. On a map, the distance could look almost convenient. Put the generators on the ridge, put the machines that need water near the crater, run cables between them. A neat little arrangement, at least while the lines are still drawn in pencil. But a base isn't a diagram. Electricity has to cross real ground through wires, switches, connectors, and control equipment. Water has to come out of the cold trap, be processed, and reach the people and machines using it. Crews or robots have to inspect the route, repair damage, and move parts between places with very different temperatures and lighting. So the cable isn't background plumbing, neither is the road. They become part of the life support system. If either route fails, the useful pieces of the base can no longer help one another. The same is true of every trip down to the ice. A shadowed crater may protect frozen water, but that darkness also changes how machines move, stay warm, and communicate. The bright ridge offers abundant energy, yet exposes equipment to the thermal punishment that comes with it. One useful place gives you power, the other gives you a resource the base can't easily replace. Mercury keeps doing this. It places helpful things close enough to tempt you, then separates them with incompatible conditions. Sunlight here, ice there, warm hardware above, cold machinery below, human work stretched across the boundary. Even routine maintenance becomes a trip between two different operating worlds. That doesn't make the layout impossible. Shorter cable runs may reduce some losses and simplify some repairs. A carefully chosen ridge, crater rim, or slope might bring the pieces closer together. But distance alone doesn't settle it. The route still has to survive, and someone still has to maintain it. Site geography becomes part of the engineering from the first sketch. You aren't choosing a spot for one building. You're choosing a connected set of small environments, each useful for a different reason, and asking whether they can function as one base without pulling its machinery and people too far apart. Could burying the vulnerable parts, or placing the habitat against a crater wall, bring those divided needs close enough together to make the whole system workable? Burying the habitat is a sensible answer. On Mercury, rock can do jobs that machinery would otherwise have to do the hard way. Put enough material between the crew and open space, and it can reduce radiation exposure. Tuck the chamber into a crater wall or beneath the ground, and it can also shield vulnerable equipment from direct sunlight and the severe temperature changes above. That's a real benefit. Passive shielding doesn't need a motor, a control board, or a repair schedule. Once the rock is in place, it keeps being rock. On a world where every active system draws power and adds another possible failure, that kind of quiet protection is valuable. You would take it gladly. But the chamber beneath it is still a spacecraft in almost every way a human body would notice. Mercury's rock doesn't provide breathable air. It doesn't hold the living space at the right pressure, remove carbon dioxide, circulate oxygen, control humidity, or turn waste and dirty water back into usable resources. NASA's life support systems manage those jobs even inside vehicles already protected from the outside environment. A layer of stone can soften what comes in. It cannot run what must happen within. Imagine walking into a room cut deep into solid rock. From outside, it looks almost reassuringly simple. No exposed walls facing the sun. No delicate habitat skin sitting bare against space. Inside, though, the quiet is full of machinery. Fans move air through filters. Pumps push water through recovery loops. Sensors watch the pressure. Seals hold against leaks. Heat still has to be carried away from people, electronics, lights, and every motor doing useful work. Even underground, the room stays alive only because all of those parts keep working together. The rock may reduce the load on some systems. It may give designers more stable surroundings and fewer hazards to fight at once. That could make an underground habitat much safer than one sitting bare on the surface. It doesn't make underground settlement pointless, and it doesn't make it solved. We would still be living inside a pressure vessel, not a self-sustaining cave where someone can open a door, put down a bag, and call the place home. Burial changes the design in an important way. It trades part of the exposed surface problem for a protected machine surrounded by stone. The outside becomes quieter, the inside remains busy. That's the contradiction. The habitat may be hidden from Mercury, while still having to resist Mercury every second. Imagine that buried habitat from the outside, a sealed entrance, rock overhead, no wind, no rain, no trees bending above it. It might look almost dormant. Inside, though, the place would be working continuously. Air would be circulating, pumps would be moving water, filters would be catching waste, sensors would be checking pressure and oxygen, and nearly every useful machine would be making heat. A human body makes heat too. So do lights, computers, cooking equipment, batteries, pumps, and the equipment that keeps the air breathable. In your home, Some of that heat slips through walls, windows, pipes, and moving air. If the room gets warm, you can open a window. A sealed habitat on Mercury doesn't get that option. Heat has to be collected, carried, and released through a system designed for the job. NASA groups much of this machinery under environmental control and life support. Its work on systems for spacecraft and the International Space Station shows how active that obligation is. Oxygen must be supplied or recovered. Carbon dioxide must be removed. Water must be cleaned and reused. Humidity has to be controlled. Waste has to be handled. Pressure must stay within safe limits. None of these jobs is something the habitat finishes on Tuesday and forgets about. The machinery is less like furniture and more like metabolism. It breathes for the crew, circulates what they need, and carries away what they cannot keep. Stop enough of that circulation, and a calm room becomes dangerous surprisingly quickly. Then there's the heat. NASA's medical and engineering guidance for life support systems treats temperature control as part of keeping people alive, while the European Space Agency's thermal engineers describe spacecraft heat as a balance that must be managed. Equipment makes waste heat, people make waste heat. That energy has to move through the habitat, reach a cooling system, and eventually escape. Rock can help smooth temperature swings, depending on the site and the design. It can also separate the habitat from the open view needed to radiate heat away. That doesn't make burial a thermal dead end. It means engineers still need a deliberate route from warm rooms and machinery to radiators or another heat rejection surface outside. Pumps, fluid loops, heat exchangers, and radiators don't become optional because the ceiling happens to be geological. There's a useful absurdity in this. The safer the refuge looks from outside, the more mechanically alive it may need to be within. Air moving, water moving, heat moving, waste moving, every hour without a weekend. So the stone above the habitat does real work. It blocks and softens some of what Mercury throws at the crew, but the shelter still has to manufacture a livable world inside itself, then dispose of the heat that manufacturing creates. Protection changes the burden. It doesn't switch the burden off. You can still imagine the base working. A few sealed rooms sit behind a crater wall near Mercury's pole, where the ground stays comparatively cool and nearby shadows may hold useful ice. Solar arrays stand where sunlight can reach them. The crew sleeps under rock, tends the equipment, and watches another day pass without an emergency. That would be an achievement. It might even be a permanent human foothold, if permanent means someone can remain there continuously while the systems keep running. But the word can mislead us. A light left on forever is still dependent on the power station. Mercury hasn't become easy in this arrangement. We've found one unusually favorable patch and built a small defended cavity inside it. The polar location helps with heat and access to possible water. The buried rooms help with radiation and impacts. Yet neither one supplies a replacement pump, rebuilds a worn seal, or repairs a circuit board after years of heating and cooling. A town can survive a broken refrigerator. This place may depend on its refrigerators, pumps, filters, valves, and computers all behaving as parts of one long life support machine. Every spare part has a history. Someone had to predict the failure, manufacture the replacement, carry it to Mercury, store it safely, and make sure a tired crew could install it with the tools on hand. Maintenance would shape daily life. Dust works into joints. Radiation slowly damages electronics. Materials expand and contract. Bearings wear. Pipes clog. Some failures arrive politely with a warning light. Others choose 3 in the morning because machinery has a sense of timing even when it has no sense at all. A successful outpost could prepare for much of this. It could keep duplicate systems, machine simple components locally, recycle water, and build a deep inventory of parts. None of that makes the idea impossible. It simply narrows what success means. The base survives because repairs receive constant attention and because deliveries from elsewhere remain dependable. So the crater wall may shelter an expedition camp that lasts for decades. It doesn't by itself turn Mercury into a practical home. The difference between a foothold and a colony is quieter than a flag planting. It appears in the supply cupboard when the last compatible valve is gone. Mercury lies close to the Sun on a map, and it's never terribly far from Earth by planetary standards. So is this upkeep-heavy little refuge at least easy to reach and resupply. Nearby sounds comforting. If Mercury sits closer to us than many other possible destinations, then surely the trip should be simpler. Less distance, less trouble. On a map, that feels almost automatic. But a spacecraft doesn't move across the solar system like your finger sliding across that map. It moves through the Sun's gravity, and Mercury sits much farther down that gravitational slope than Earth does. That changes what the flight asks of both the spacecraft and the people guiding it. Imagine riding a bicycle into a steep valley. Getting closer to the bottom takes very little persuasion. Gravity keeps adding speed. The awkward part comes when your destination is a tiny driveway halfway down, and you need to enter it gently instead of flashing past with the brakes smoking. A spacecraft falling inward behaves in much the same way. As it gives up distance from the Sun, it gains speed. By the time it reaches Mercury's neighborhood, that extra speed can work against the very thing the mission needs to do: stay there. Mercury's own gravity is relatively weak. It cannot simply grab any spacecraft that happens to pass nearby. The craft has to approach slowly enough for Mercury to capture it, or it must burn fuel to shed the excess speed. That is why the European Space Agency describes arrival at Mercury as a problem of slowing down, not merely covering the distance. You can almost feel the reversal in your body. The destination grows larger ahead of you. The Sun pulls harder. Your speed keeps rising. Everything looks like arrival, while the motion itself is making arrival more difficult. Mission planners can manage this. They can use carefully chosen paths, planetary flybys, long arcs, and repeated braking maneuvers. Different spacecraft may handle the trip in different ways. Mercury is not unreachable, but none of those solutions restores the simple comfort of nearness. They exist because flying straight inward would leave the spacecraft carrying too much speed relative to the planet. So distance alone tells us very little about how easily supplies can be delivered. The useful measure includes energy. How much motion must be changed before the cargo can enter orbit, descend safely, and become something the people below can actually use? Mercury may be nearby in kilometers. Operationally, it sits at the bottom of a slope. A supply craft can fall almost all the way to its destination and still arrive too fast to stay. Imagine making it all the way to Mercury, seeing the planet fill the window, and then watching it slide behind you because you arrived too fast to stop. You reached the right place, you just couldn't stay there. That's the arrival problem in its most physical form. As a spacecraft travels inward, the Sun pulls it faster and faster. Mercury is moving quickly too, but unless the spacecraft sheds enough of its own orbital energy, the two don't meet like a truck easing up to a loading dock. The spacecraft comes rushing through. ESA puts the problem plainly. Without slowing down, it won't be captured by Mercury's gravity. It will fly past. So mission design gets built around losing speed. A spacecraft may spend years making carefully arranged passes by planets, using their gravity to reshape its path a little at a time. Engines can help, and future propulsion could improve the choices. But every delivery still has to solve the same awkward problem. Reaching Mercury's neighborhood isn't the same as joining Mercury. For a scientific probe, that can mean a long and carefully planned flight before the instruments ever begin their main work. For a supply system, it becomes a recurring bill. Every food container, replacement pump, medical kit, and pressure seal has to follow a route shaped by that difficult arrival. More propellant may mean less cargo. Longer flight plans mean slower replacement cycles. Narrow launch opportunities make it harder to send something exactly when it's wanted. A late shipment may have been committed to its slow approach long before anyone knew which part would fail. And cargo cadence becomes critical when people are waiting at the other end. A settlement can't treat each delivery as an isolated triumph. It needs a rhythm it can trust. Filters wear out, motors fail. Machines develop small, irritating faults that become serious when the nearest warehouse is another planet. If the route is slow and expensive, you stock more spares in advance. That adds mass, More mass makes delivery harder. You may need backups for the backups, simply because the next useful shipment can't be hurried across the gap. The arrival problem quietly reaches backward through the whole operation. This is why capture isn't a footnote after the flight. It shapes how much arrives, how often it can arrive, and how much protection a crew needs against delay. Better engines may lower that burden someday. They don't make the burden imaginary. Each successful freighter would approach a world it had spent months or years chasing, then perform the careful work of not becoming a bright metal speck that skimmed past Mercury and kept falling around the Sun. Once a base is established, logistics can sound like an accounting problem. Fuel costs more, cargo costs more. Keep the supply budget large enough, and life inside the habitat carries on. But the people living there won't experience logistics as a line in a budget. They'll experience it as a pump that has started making the wrong noise. On Earth, a broken pump is inconvenient. Someone checks the model number, finds the part, and arranges delivery. On Mercury, that ordinary replacement may be months or years away, with every kilogram competing for space aboard a difficult mission. The planet is distant in a way that a map doesn't quite show. So is the spare bearing sitting in a warehouse back on Earth. That changes how every machine must be designed. The cooling equipment, radiation shelters, power systems, air recyclers, water loops, seals, tools, and medical devices all need repair plans. Crews would need parts they could swap, materials they could reuse, and enough local manufacturing to make certain failures survivable. Even then, manufacturing equipment has its own cutters, filters, electronics, and failure points. A machine shop doesn't remove the supply chain, it becomes another demanding link inside it. And this is where a small shortage can become something much less small. A damaged valve may leave less cooling capacity. That puts more strain on the remaining hardware. The extra strain shortens its life, while the next suitable part is still waiting for a launch, a transfer window, and a successful arrival. Nothing dramatic has to happen at first. The base simply loses options. A future settlement might reduce this weakness with better propulsion, larger stores, interchangeable parts, local industry, or several habitats able to support one another. Rescue wouldn't be impossible under every design, but every layer of independence would require more equipment, more power, more maintenance, and more material delivered or produced locally. So Mercury's transport problem never stays outside the door. It follows the crew into the workshop, the clinic, the power room, and the quiet moment when someone opens a cabinet and finds that the one component they need isn't there. Once distance can turn an ordinary repair into a threat to the habitat, what is the fairest answer when we finally put Mercury's whole bill on the table? You can imagine the outpost now, not as a bright dome dropped onto a convenient patch of ground, but as a long, tense arrangement near Mercury's pole. Somewhere below, ice waits in permanent shadow. Somewhere nearby, sunlight reaches high ground and offers power. Between them sit cables, machines, storage tanks, sealed rooms, and people who need all of it to keep working. Each part looks like an answer. The shadow protects the ice. The light feeds the power system. Buried or shielded spaces protect the crew. Stored supplies cover what the settlement can't make. The transport chain reaches back toward Earth when local repairs and reserves aren't enough. But those answers don't stand alone. The ice is useful only if machines can reach it, extract it, clean it, and move it. Those machines need power. The power system needs maintenance and protection. The habitat needs cooling, shielding, air, water, spare parts, and enough sealed volume for people to live without wearing one another thin. The supply line supports every one of those systems, while every delay asks the base to become more independent. This is where Mercury becomes difficult to judge fairly. You can't take its best feature, admire it in isolation, and call the place workable. You also can't take one ugly cost and declare the whole idea impossible. The useful unit is the base itself. One coupled system stretched between darkness, sunlight, shelter, machinery, and home. That coupling creates dependencies you don't notice when the pieces are kept in separate piles. A stronger power system may reduce one risk while adding equipment that needs repair. More shielding may protect the crew while increasing excavation and construction work. Larger stores may soften a delayed shipment while demanding more delivered mass, more storage space, and more careful monitoring. Even local production, the usual answer to dependence, arrives with its own appetite for tools, energy, feedstock, and skilled hands. Mercury has little patience for any subsystem designed on the assumption that another subsystem will be easy. Power can't assume maintenance is simple. Maintenance can't assume parts will arrive quickly. Life support can't assume power never falters. The crew can't assume the habitat will always give them time to improvise. None of this proves that a polar base can't be built. We don't have a finished design here, and the loophole remains physically real. There are places near Mercury's poles where several severe problems become less severe at once. But once every advantage and every cost is forced into the same plan, the bargain changes. The loophole is still there. It is simply carrying a frightening amount of debt. That debt forces a change in terms. Mercury may offer a foothold. That doesn't make it a frontier. The distinction sounds small until you imagine the place. A foothold is one defended outpost, built around a narrow set of conditions that happen to work. Its machines are chosen for that exact site. Its crew follows strict limits. Supplies, spare parts, and specialist help come from elsewhere. If something important breaks, the whole plan may bend around that failure. A frontier asks much more of its surroundings. People need room to expand without rebuilding the bargain from the ground up each time. They need backup systems, replacement parts, medical care, transport, storage, and enough spare capacity to survive ordinary mistakes. A damaged cable shouldn't become an emergency for everyone. A delayed shipment shouldn't threaten the air. Maintenance should be inconvenient, not existential. That's what margin means here. You have more power than today requires, more cooling than the habitat normally needs, more ways to reach shelter, more time to diagnose a fault, and more than one person who knows how to repair it. Redundancy means a single failure stays a single failure. Ordinary recoverability means people can have a bad week without turning it into their last week. A carefully placed base on Mercury might achieve some of that within a tightly controlled boundary. It could be scientifically valuable. It might support instruments, prospect nearby deposits, or test equipment that can't be tested anywhere else. None of those possibilities should be dismissed, nor should they be inflated. The temptation is to treat any human survival as proof of settlement. Keep a crew alive for 6 months, and the planet starts appearing on maps as somewhere humanity can live. But we can keep people alive in submarines and Antarctic stations. We don't confuse either one with a new world ready to receive a city. Scale changes the standard. 10 people can depend on rare expertise and carefully scheduled cargo. 10,000 people can't live as a permanent emergency operation. Families, workshops, clinics, warehouses, and local transport bring ordinary life with them. Ordinary life is messy. It needs slack. Mercury's polar loophole may be enough for a narrow machine with people inside it. That is a serious engineering possibility, and perhaps one day a worthwhile one. But it proves only that the machine can keep running under protection. It does not prove that Mercury offers the margin, redundancy, and recoverability of a practical settlement. So the plain answer has become smaller than the old colonization language suggests. Humans may someday hold a foothold on Mercury. Mercury would still not be a human frontier. That leaves us with an answer that's less tidy than yes or no, but much more useful. Could human beings survive on Mercury? Maybe. In a carefully chosen polar niche with deep shielding, reliable power, stored supplies, and machines built to tolerate very little mercy, a small crew might live there. The loophole is real. It deserves to be treated as engineering, not fantasy. Would Mercury be a practical place to settle? Probably not. The trouble is that every answer creates another bill. Hide from the sun and you lose easy access to sunlight. Build where temperatures are manageable and useful ground may become scarce. Depend on buried ice and mining. Purification, storage, and recycling all become parts of the life support system. Shield people underground, and construction gets harder. Bring more equipment for safety, and every launch, landing, repair, and replacement grows more demanding. Nothing there gets solved once. It gets held in balance. You can imagine the polar base now, not a shining city waiting to spread across the landscape, more like an expensive machine perched inside a hostile contract. Every wall, cable, radiator, battery, and water tank is part of the agreement. Keep paying every term, and people may stay alive. Miss enough of them at once, and Mercury collects quickly. Future technology could lower some of those costs. Better recycling might reduce cargo. Better robotics might make repairs safer. Better power systems might give a base more breathing room, but those improvements wouldn't move Mercury farther from the Sun, soften its temperature extremes, create an atmosphere, or give settlers an easy route home. The fundamentals remain. So we don't need to pretend the answer is binary. A flat no would ignore a genuine physical opening at the poles. An easy yes would hide the enormous structure required to use it. Mercury earns a narrow maybe for survival. For practical settlement, it earns a much firmer no. And that may be the calmest way to leave it. Somewhere near the pole, in a patch of permanent shadow, people could perhaps keep a small light on. But the light would belong to the machine protecting them, not to a world becoming comfortable around them. Mercury might permit a human presence. It would never make much of a fuss about keeping one. Imagine that bright crater rim one last time. Sunlight strikes the high ground with almost no mercy. A few steps lower, the floor remains black and bitterly cold. Somewhere between them, pressed into the slope and buried under shielding, a habitat might just fit. That narrow strip is Mercury's best offer. The shadow could protect stored ice. The bright rim could provide long hours of solar power. The ground itself could cover living spaces against radiation and tiny, fast-moving debris. With careful placement, engineers might turn 3 hostile conditions into something useful. But useful isn't the same as friendly. The ice still has to be found, mined, cleaned, and carried. Electricity still has to cross from the light into the dark. Radiators must release waste heat without freezing other parts of the system. Seals must hold. Filters must keep working. Pumps, cables, batteries, computers, and air systems all need repairs. And every repair has to happen on a world with no air, no easy resupply, and very little room for improvisation. That's the awkward bargain. Mercury offers a loophole, then sends an invoice for using it. A small polar outpost may be possible someday. You can imagine a few people living there for months, perhaps longer, supported by machines designed with extraordinary care. They might study the planet, operate equipment, and learn how to use local ice and rock. Future technology could make all of that cheaper, safer, and less dependent on Earth. It could improve the bargain. It wouldn't turn Mercury into a home in the ordinary sense. A home can forgive a broken heater for a while. It has air outside the walls. Water arrives without being mined from ancient darkness. Help doesn't need to cross tens of millions of miles. On Mercury, survival would remain an active process. Stop the process, and the place quickly becomes what it always was. So the plain answer is this. People may one day survive near Mercury's poles. They may even build something permanent enough to appear settled from a distance. But a heavily engineered foothold isn't the same thing as a world that can support us at scale. The crater rim gives power. The crater floor may give ice. The slope between them may give shelter. None of those gifts arrives ready to use, and none removes the vacuum, the radiation, the harsh temperatures, or the distance from everything that keeps us alive. Mercury may allow a human presence. It probably won't welcome one. And perhaps that distinction is enough. We don't have to make every reachable world into another Earth. Sometimes the achievement is simply learning where life can hold on, with good engineering, patient maintenance, and a clear understanding of the cost. A small habitat might remain there beneath the ground, wedged between sunlight and shadow, warm inside, black sky above, machinery humming because it must. A foothold then, not quite a home,